First we develop the DC model, then we develop the AC model, we developed RPi, we developed GM for the Pi model, and we were in the process of converting the Pi model into the T model. So today we're going to continue that, convert the Pi model into T model, and once we have done that, then we'll do a series of examples of how to use the T model for small signal analysis. Okay, that's what we're going to do. So first of all, from the Pi model, how do you get the T model? First, the Pi model, which we developed the last time, and we had a resistance here. These all refers to small signal model. Okay? And then we had a current source here. This was your base, this was your emitter, this was your collector, this was RPi, this was IC. IC is flowing into the collector, IC, which is equal to, you can write as GM VBE. Also, initially we wrote equal to beta IB. So IB is the current flowing into the base terminal, which is IB. Okay, and you can draw a line here this way, showing the current flowing into the emitter terminal, I, which is the sum of the two. Okay. And what is the relation of RPi with GM and beta? They are all related. This all related.
Beta over GM.
Beta over GM. Okay. So RPi we have reduced equal to beta over GM. Okay. So from this, we are going to try to convert into T, which we were half the way here, last time. So we're going to start everything and do nicely and complete it. So the first step, we are going to do it in few steps. So the first step is to do this. This is your emitter terminal here. This is your base terminal. And this current source that we were feeding here directly into the emitter, we will take this current source, first feed it into the base, and then take it away from the base. And then I will take it away from the base. So this is your collector, this is your base, this is your emitter, and this current source is the same current source, IC. IC equal to GM VBE equal to beta IB. Beta, we know this is either beta AC or beta DC, which we assume to be the same for most of these applications. Okay, and this is also the same thing as this, which is IC equal to GM VBE equal to beta IB. Okay, and this is your IB coming this way. And this is your RPi. Okay. So now if you look, you see this current source here, you give here, you apply this current source here, and then take it away. So there is no net change. So if you sum up the current, all the currents, IB here, IB this way, okay, IC this way, and again IC this way. Then here if you sum, you see IB coming, IB going, IC coming, IC going here. So there is no change in the actually the sum of the currents. Here you have IB coming, IB going this way, IC coming, IC going this way. The sum of the current is here is still equal to IB plus IC. IB plus IC. So here you have IB plus IC, here you have IB plus IC here. So nothing is changed with respect to here. And at this node, you are applying, providing the current IC and then taking away. So if you sum all the currents, You see the currents coming, IB coming in plus IC coming in equal to IB coming out plus IC coming out. Okay, so you can cancel this. Is IB coming in, IB coming out. If you again do this way here at this node, look at here, you have IB coming in, and here again IB going out equal to IB. IB coming in, IB going out. So if you add them all together, IB plus IC coming and IB plus IC coming and IB plus IC leaving. So there's no change actually. Okay? So then you can see here, this current source here, what can we do with this current source here? So this current source, you can see this voltage. What is this voltage between here and here? What is this voltage? Between the base and emitter, what is this voltage? Algebraically.
VB.
VB. So this voltage is VB. From here to here is a voltage VBE. And what is this current source? GMVB. So what you have here is a current source. Okay. What you have here is a current source. You have voltage, voltage B, voltage across base and emitter here, okay, and then you have a current source. So between here and here you have got VBE, and then between also B and E you have a current source which is GMVB. Okay, between here and here you have this current source which is GMVB across a voltage which is VB. Correct? So, can I change this to this now? Where I have this B here, I have this E here, and between this I have a voltage VBE, and then just change it into a resistance only, whose value is 1 upon GM. I convert this into a resistance, just a resistance whose value is 1 upon GM. What is the current flowing here? What is the current flowing from here to here?
GMVB.
GMVB. What is the current flowing to here to here?
GMVB.
Okay, is everybody clear? Back there, this has no difference between these two, but this looks much friendlier than this one, isn't it? Current source, we have question. This is dependent current source. This is not dependent. It's just resistance, whose conductance is GM, whose resistance is 1 upon GM. So we can just remove this from here. Just remove this and put this thing here. 1 upon GM. And then this R pi equal to beta by GM. Okay. So you have a beta by GM in parallel with 1 upon GM. Which one will dominate? Which one will dominate over there? Which one will dominate? You have this one beta by GM. Beta can be 100, 200, you know. And this is 1 upon GM, this is beta by GM. Which will dominate?
Beta over GM.
Beta will dominate? How can this is in
Because-
parallel? You have two resistors in parallel. One is much larger, 100 times larger than the other one. Which one will dominate?
Small one.
Smaller one, isn't it? Who said that? Okay. Isn't the smaller one going to dominate? If you take a resistance which is 100K, okay, 100K, put in parallel with it another resistance which is 1K. So what is the overall resistance? Approximately, what is it? 100K, 1K. How much is here? Approximately. Don't have to be exact, you know. Can I just throw it away and say this is 1K? Hmm? Can I? I don't see any response from the back. Can I? Can I not? Can I? You're sure? You're happy for me to do it? No objection? Can I do it? Can I do it? Okay, so because everybody agree and it seems everyone understand why. So I will do this thing here. I know this beta is close to 100, 200. This is 1. So you can just throw it out. Then this is your model. Yeah? This is your T model. This is your T model. Okay, this is even simpler. So what does the T model look like? It's very simple. T model looks like you have one line coming here, and then you have a resistance here 1 upon Gm, and then you have a current source here coming in here, which is IC equal to beta into IB equal to Gm into VB. This is your base, this is your base, this is your collector, this is your emitter. Here your IB is coming, small signal current. Here your IC is coming, okay, and adding together with IB, which is equal to your IE, which is approximately equal to IC. IB is very small compared to IC, so approximately this is equal to IC. So isn't this somewhat easier looking than this one? What do you think?
Yes.
Bit easier looking. So we are going to use that in most of the things that we do in this level. Sometimes pi may look better, in some other analysis, but what we will do is that we will mostly use the T model. So this is the T model. T model. And what is the current flowing through here? IC is beta IB, isn't it? So this you can also say 1 plus beta IB. And 1 upon Gm is sometimes referred to as RE. Okay? As emitter resistance. If you see here between base and emitter, if you call this current IE, okay? If you call this current IE, then what is RE? RE equal to the current VBE, voltage VBE divided by IE. Put that here. If I call this RE now, emitter resistance, then this is equal to the voltage, which is VBE, divided by the current flowing through here, which is IE. Then this is equal to, approximately equal to VBE divided by IE is approximately equal to IC, which is equal to what? Is equal to what? VBE by IC equal to what? VBE by IC equal to what?
GM.
GM, exactly. So this is equal to 1 upon GM. Okay. GM is conductance, RE is resistance. Okay. So that's why 1 upon GM is sometimes referred to as RE. And if you look at the textbook chapter 7 BJT Malvino's description, then they call R pi equal to beta into RE or RE prime. Sometimes RE is also called as RE prime, which is equal to 1 upon GM. So if you look into the textbook, like Malvino, you see that in the pi model, this is called beta RE or beta RE prime, equal to beta RE prime. And RE prime is nothing but 1 upon GM. Okay? So you can call this R pi, you can call this beta by GM, you can call this beta into RE, because RE is equal to 1 upon GM. Okay? Is it clear? Is it clear, everybody? You can call this R pi, you can call this beta by GM, and since 1 upon GM is called RE or RE prime, you can also call it beta into RE or beta into RE. See? So one person have so many names. Jack, John. What else? Jim, Jeff. Hmm?
Joseph.
Joseph. You're Joseph? So if so many names here, you see, so name really doesn't matter. What matters is the content. Okay. So this is what we can call all of these, and this is the T model. So we will try to keep things simple. We just call this one of GM, IB, IC. And do you know how you can get? You got the pi. From the pi, you got the T. From the pi, you got the T. Do you know how you can get your pi back from the T? Do some reverse engineering. Okay, so you can see here, this thing, all the time when you change entities, you must make sure that the terminal current doesn't change. As long as you don't violate Kirchhoff current law, Kirchhoff voltage law, nobody can tell you anything. Okay, so I didn't violate Kirchhoff current law or Kirchhoff voltage law when I transformed into the T model. So I'm going to transform this T back into the pi, which is not really necessary, just to show you. Okay? You can see here what you can do. You see, look at this here. This is equal to 1 plus beta 1 upon Gm. So you can call this voltage drop here. So the voltage drop here is how much? 1 upon Gm into 1 plus beta IB. This is the voltage drop here, correct? The voltage drop between the base and emitter. This is equal to VB. Correct? VB equal to this resistance into this current. Or if you want to call 1 upon Gm as RE, then you can call it RE into 1 plus beta IB equal to VB. Okay? So here your resistance is RE. Okay, resistance RE, and your current is this, 1 plus beta IB equal to VB. So this voltage equal to this current into this resistance. But does it make any difference if I say this is equal to RE 1 plus beta into IB, okay, into VB. Okay, I'm saying this resistance into this current equal to this VB. Or it really doesn't matter if I say this resistance into IB equal to VB. Does it matter? It doesn't matter. So I'm going to just do this on this. Okay. So what I'm going to do is do a surgery here. Okay. And then I take a resistance here, and this resistance equal to RE 1 plus beta. Okay, and this IB current flowing through here, IB, and then take this current source here, put it here, IC equal to beta IB equal to GMVB. This is your base, this is your collector, this is your emitter. You got your pi network back, but you might argue that you have a 1 here. Before you had beta RE, now you have 1, but 1 really doesn't matter. So I can just call it approximately equal to RE into beta, which is equal to again your R pi. So you can see just by changing the appearance of the expression, you can go from here to there. Okay? And as long as you don't violate any Kirchhoff current law or Kirchhoff voltage law, you are absolutely fine. Okay? So all this is it clear to you? All of this before I go start using the T model to solve some AC small signal models? Is all this clear to you? Everybody? Every one of you? Clear? What is your name? Daniel. Is it clear, Daniel?
Yeah.
What is your name? Is it clear, Andrew? I can't ask everybody, I'm just randomly speaking. What is your name? Nick, is it clear, Nick? So here, Nick, is it clear? Come. Okay? So you practice that. You practice it now. Have you done it now? Okay, everybody please write it down. Yes, everybody write it down. What's your name again? Is it clear? Oh, can I have your name again? Yes, is it clear? Is it clear? Is it clear? Sure? These people are very far off. Is it clear? What is your name? What is your name? Are you sure? Okay, Jean, what didn't you understand?
I'm just. Just trying to screen this part here. That comes parallel.
This is the same node, just one point. See, there is no resistance here. So all of this is just one point. That's how it's done.
So it would be the same as just if there.
Yeah. That's the same point. Same point. Yeah, what did you understand? Yeah, tell me, yeah. Oh, he's taking photo. Tell me what? Which one? This one? This one? Yeah, so this was beta by GM. This is very large compared to this. They are in parallel. So when two resistors in parallel, the smaller one only. That's why we keep this similar. What about GM? Because it came from this. What about GM? Because it came from, you see? Let me write it again. From here, it came from here. See? Before this, you had this here. This thing was sitting here. So you had GMVB. So this thing here, across voltage VB, GMVB, VBE. Okay. So if you remove this and put 1 upon GM here, then this is a resistance. GM is conductance, 1 upon GM is resistance. Then what is the current flowing through GMVB? Because GM is conductance. The current flowing through here is GMVB. Isn't it? So it's the same as this. So that's why I just remove this and put 1 upon GM. Because GM is the resistance conductance, 1 upon GM is the resistance. So I'm just representing it as a resistance. GM, but I'm calling it 1 upon GM to show its value as a resistance. No, because this is 1 point. Yeah, no, it's just 1 point. 1 point. Because this is why no current flow? Because this and this has same potential. If 2 points is same potential, no current flow. If 2 points, if you're aware, just aware, this is 5 volts and this is 5 volts. How much current flow through this? This is 5 volts here, this is 5 volts here. How much current flow? Current flow. If this is 5 volts and if this is 5 volts, how much current flow? Zero. Exactly. So that is okay, so I assume most of you have understood it now. And yeah,
That's pretty good on that last part again. So how do you from this? You say the points are the same. So
same, exactly, yeah. So I will explain to him, if this is 5 volts and this is 5 volts, what's the current flowing through here?
Zero.
Exactly, 0.
Yeah.
These two, if you consider them as separate points,
Yeah.
they still have the same voltage. So it doesn't matter whether you consider them. If you take one line like this, put many lines, and this is 5 volt, this is 5 volt, this is 5 volt, this is 5 volt, this is 5 volt. It's the same point. Nothing is going to happen. No current going to flow this way. Nothing will flow this way. Nothing will flow this way. Okay.
Can we technically get rid of that that certificate line on the top then, if it's going to be the same?
This one?
Yeah, if it's going to be the same potential.
Yeah, you can take it off. Yeah, you can take it off now. Because it doesn't matter, because you are this current, you're showing another current source flowing this way, see. But the purpose I put it this way is to make them together, see. That's why I put this line, to put them together. But it doesn't violate any circuit law. As long as it doesn't violate any circuit law, you can connect anything to anything. Okay? Okay, so can I erase all of this? Have you written everybody up? Written up? Okay, so I'll just erase all of this and go back to my P model and start solving some of the problems that we need to solve. So we will go back to our original simple circuit. Okay. VBB, RB, emitter, base, collector, and then you have the resistors here, RC, and you have VCC. Okay. So this is the simple circuit that we know, okay, that we have been working on as a switch and also operation as a amplifier in the forward active region. Okay. And if we are going to use it as amplifier, we have to apply a small signal, which you discussed last time, as going maybe through this way, through a capacitance, and you have V in here and ground. So this small signal coming up in, and then if you don't like the DC, take it out into a load resistance separately. Then you could put other capacitors here, and then you put RL here. Okay. So this now is a problem which contains both DC and AC. Okay. It can start from saturation, from using as a switch, then using as amplifier, then working out the small signal operation. Okay. So whenever you get a problem like this, the first thing you have to do, if you are trying to use this amplifier, is to solve the DC bias point first. So if you want to solve the DC bias point first, which you know very well, is what you do is that you find, do you need these circuits for the DC operation? Do you need this and this? Do you need? You don't, isn't it? For DC you know this. So what you do is that when you get a problem, you break it up into two problems. Okay. So one is DC equivalent circuit. DC equivalent circuit, and other is AC equivalent circuit. Okay. One, what is the DC equivalent circuit? Two, what is the AC equivalent circuit? Number three, AC analysis. AC analysis by inserting the small signal model into the AC equivalent circuit. Okay, so these are the three things. When you have a problem like this, operation as amplifier, these are the things you have to do. DC equivalent circuit, why? Find the bias point. Find ICQ, VCEQ. Okay, you have to find the bias point. AC equivalent circuit is the middle path in progression to doing the AC analysis. What is it doing? What is it? You can't do anything in my lecture. It's not allowed. Have you written down? No, you got it. Come. Leave yourself. Leave yourself. Is there a chair here? You sit here. Yes, sit here. You sit here. Yeah, write everything down. Write everything down. Okay. Got it? Okay, so how to do these things? You already know all of this, most of it. For this, what is the DC equivalent circuit? Who can draw out of this the DC equivalent circuit? Okay, draw here the DC equivalent circuit. Who can draw the DC equivalent circuit? Who can draw from here? DC equivalent circuit? Yeah.
So it'll just be pretty much all that, just without the AC stuff, right?
Hmm?
So we'll just build that just without the
Yeah.
AC stuff. So that's
Yeah, very simple. Yeah. just follow Jacob, huh? How to do it. Thank you. Done. So this is all you have to do to develop your DC equivalent circuit is neglect the part which concerns AC operation. So you don't need this, you don't need this. Because the DC cannot go through this, DC cannot go through this, so that's not a part of the DC circuit. Okay? So now you got your DC equivalent circuit. Next, from this you have to find the bias point. So who can do that? Find the 2 points, extreme points. One is on the x-axis, one is on the y-axis. Connect them, choose the middle point, and determine the bias point. Who can do that? Over there, third row, over there. Who can do that? How to draw the load line, and show the 2 extreme points, and then show me the beams. You've done well. You will do it? Just draw the line, no? The load line. Yeah. What's the name again? Marco. Marco Rubio. Yeah, give them the names. What is that called? Okay, this is x-axis. What is called? VC, isn't it? VCE. VC. Make it large, because this is all larger scale. So big C, big. No, this is capital. Yeah. So I see over there. Okay. I see. Okay, and then this is point what? This point is how much? Yeah, what is the value? This is the point where transistor is off. No, current is 0. What is the voltage here? This is how much? You see here, there is no current flowing here. There is no current flowing here. When this transistor is off, there is no current flowing here. Then what is the voltage between here and here? Yeah, how much is that? There is no 50 here. I don't know. Yeah, you see here, just look at the circuit. VCC, exactly. Just put VCC.
So, did we have to give a value for that? Or
if I give you, I haven't given you a value. So that's why, if I don't give you a value, you can't put a value, no? It's algebraic at the moment. Later on, we'll do example with values. Okay? So, what is this current? This is the current which is completely on. That means the voltage drop between collector and emitter is 0. Completely on, switch. Then what is the current flowing through here? When this switch is completely on, see this line VC is 0. This is the line where VC is 0. VC 0 means this is completely saturated. VC is equal to 0. So if this voltage is 0, you can do the KVL along this path. KVL along this path, this voltage is 0. Then what is this current? Algebraically. You have voltage VCC here, and this is ground, and this is also ground, and you have a RC here. So you voltage VCC, voltage 0 volt. Exactly. VCC over R. Good. You feel better now?
Sir, RC.
Yeah.
That's okay, you know. Give him the benefit of doubt. Yeah, so everybody is preferred, they want half, they don't want full, you know. Full is dangerous here, you know. So you want half of it. So you do half, and this half is what? VCC by 2 RC. And this approximately is VCC by 2. Okay? So your ICQ equal to VCC divided by 2 into RC, and in VCEQ equal to VCC by 2. So you've done this. Okay? You've done this. So from this, when you do the DC analysis, it's also a good idea to get your GM, because you know when you do your small signal analysis, you will need this GM here. See? You need this guy, GM. And we found out, we deduced previously that GM equal to what? How is the GM related to the large signal biasing current?
IC over BT.
IC over VT. So this is now this will be ICQ over VT. So this is going to be equal to VCC by 2 into RC into VT. So VCC will be known, RC will be known, VT is always known, so GM will always be known. And this is equal to current by voltage in mho. Okay. So this completely solves what we need. We get the from the small signal, from the large signal model, from the large signal equivalent circuit, we get our GM, we get our bias points. From the bias point, we get our GM. So because we need the GM later, we have to get it now from the biasing point. Is it clear? So that's what we have to do. So next, you have to do this, you know, AC equivalent circuit. So this is slightly tricky. So what is the AC equivalent circuit? Who can draw the AC equivalent circuit here? AC equivalent. So how to extract your AC equivalent circuit from here?
Do we get rid of the battery sources that don't change?
Yes. Okay. So let's, as what is your name again?
Heinrich.
Henrik. As Henrik is giving us his, so I won't have to lecture much today because Henrik is already telling me what to do, you know. So I'll just follow Henrik today. Okay. So as Henrik said, this voltage battery, you see, does the AC change here? Is there any AC variation here? No. So as far as the AC is concerned, this is ground, you know. So this is, as far as the AC is concerned, this is ground. Does the AC change here? Any change here? No. No. So as far as the AC is concerned, this is ground, you know. Okay. These are large capacitors. What is the impedance of this capacitors? So this capacitance, say you call it C1, you call it C2, and these are microfarad, very large, you know. So X C1 equal to 1 upon omega C1, and X C2 equal to 1 upon omega C2. So C1, C2 very large. What is the impedance? What is the reactance?
Very small.
Very small, isn't it? So this is approaching 0. This is approaching 0. Okay. So if this reactance approach 0, if this reactance is 0, do you need the capacitance here anymore? No. Just short them. Short them. That's all you have to do to make your AC equivalent circuit. So who can do it now? Yeah, draw it nicely. From this figure, draw the AC equivalent.
So is that just top bit?
We discussed already, you should know everything now. No? This is, there's no AC variation here, so this is like ground. As far as AC is concerned, this is like ground. This is ground both for AC and DC. This is a short because the impedance is very small. This is a short because impedance is very small. So just implement it. What is your name again?
Sungyang.
Huh?
Sungyang.
Sungyang, yeah, Sungyang. Okay, Sungyang will do it for us. All you have to do is redraw the circuit and put the grounds and the shorts, that's all. Can you kindly put your names, Yeah.
Why do we short the capacitors in the AC?
We short it because the capacitance, the impedance of the capacitance reactance is 1 upon omega C1.
Okay.
And no matter what the capacitors are, these are very large, but omega at very high frequency, this is almost zero. If you make this very large, this is zero. So if this is zero, it's like aluminum, a piece of metallization. So you just skip it with metals.
So is that something that we assume when we look at these circuits? Then? Is that just something we assume when we look at these circuits?
Yeah, when I ask you to do AC analysis,
yeah,
the whole purpose of putting this capacitor is just to block the DC and allow the AC.
Okay, sweeter. Thank you.
Sorry.
What is the resistance? This resistance. And then this is the ground, you see, so you should show a ground on the top. Yeah, just draw ground over there, doesn't really matter. Yeah, okay. And then this is the short. Yeah. Short, and then put RL and then go to ground. Okay? Okay. That's R. Okay, just put V in, label here V in. Done. Do you understand what you did? Okay, good. So this is what you have to do for AC equivalent circuit. Drawing could have been a little bit better though, but I guess everyone understands what it is. Okay? In art can be a little bit better. Okay? So you can actually draw a little bit better. So somebody who draws better is going to draw now the AC analysis, AC model, and insert the AC equivalent circuit here. Okay? This one has a T model. Remember the T model? Again, I will draw it again for you. 1 upon GM. IC, IB, IE. This is IC equal to beta into IB equal to GM into VB. So this is the T model. So what I am asking you to do now is this part 3, AC analysis by inserting the small signal model into the AC equivalent circuit. So this is your AC equivalent circuit, and insert this T model into this part. Okay. Insert the T model. insert the T model, then you will be ready to do the essay analysis. So, do you want to do it now and go for a break, or do you want to come back and do this?
Do it now.
Do it now. Okay, who can do it now fast? Who can do it now fast? No, Kishka has done once. I don't want to bring her back again. I think she knows. Rangi? John will do it. So you make a nice, beautiful diagram. Erase everything. Erase everything. Make a beautiful diagram, and insert the T model.
Erase everything.
Erase everything. Or if you want to keep it for your reference, then you can draw it here.
Yeah.
Yeah. It just erase everything here. Then. Not because we need this. You can't erase this. We need this. Maybe do it here. No, the rest is here. It's not. 1 upon GM. What is it? 1 upon GM. Just keep the names now. Excellent. Beta ID. Go to GMDB. Very good, excellent. So this model is not going to give you. You will not be provided this model in the exam. You have to remember it really, this T model or pi model. You have to remember this. You have to remember that this is equal to IC equal to beta IB, GMVB. This is not going to be given in the exam in any sheet. So you have to actually be able to memorize these few small things, Okay. So this is very correct, So when we come back from the break, we'll find the gain. The V out is here. This is your V out. Small signal output, this is small signal input, then we want to find out the gain, which we'll do after we come back from a 10-minute break. Okay? Should have a fountain in every classroom. What do you think?
People get up in the middle of your head, then drinking, and slip.